So just as we did last time, we have triangle ABC, which there is the incenter, and let's write the radius of the incenter as r, the small r, and also we have the excenter, and let's write the length of the excenter as this big R right here. And also, we can also find the excenter. I'll draw one more triangle ABC, where we extend this, and then the circle that meets these three lines, I'll name it B underbar A. Or actually E underbar A, this is the excenter. And I'll write the length of E underbar A as big R underbar A, okay? So from here, we have basically 7 ways to get the area of this triangle. ABC equals, first one is, as you would all know, height times base times 1/2. The other one is AB times AC times, name this angle here as alpha, sine alpha times 1/2. And then small r over 2 times A plus times AB plus BC plus CA. Also, and I'll do the proof a little bit later. After I lay out all the methods to get the area. And also, this is the one using the excenter. This is the one using the incenter I, and the next one we'll use the excenter by stating it in this way, and the next one actually has a name. This one's called Heron's formula. This and s, this small s here, equals the length of each of these sides added together and divided by 2. And also another way is I will put a coordinate to each of the points here. I will name A as small a comma small a1 comma small a2, small b1 comma small b2, small c1 comma small c2, and then it actually becomes this one is called the Shoelace method, where you multiply this times this plus this times this. So the reason why it's called the Shoelace method is that you multiply in this order and then just add them all together. You multiply in the other order and add them all together, get the difference between the two divided by 2, and that is also the area. So these are basically the ways in which we can get the area of triangle ABC. Well, it's very boring to just memorize math, so let's try to prove each one of them. But before I present the proofs to you guys, you want to have a bit of time to work on the proofs. Do you want to find the proofs yourselves?
Of course we do.
Okay. Proof for any one of these?
Yeah, maybe.
Which one? Which one? Okay, then I'll just go on with the proofs. Is everyone fine with it? And also, I solved that one, so after I finish explaining about these, I'll give you the questions. And in the meantime, if you're interested, you can, I'll explain you the solution for that. Yeah, if you want to prove these, you could. Well, first, before we go on to these, let's talk about like a really simple and straightforward lemma. So lemma is like a kind of like a mini theorem used to prove other theorems. So first, if the height is the same, if the base is the same, if any triangle is formed from these two parallel lines, their area would always be the same because triangle's area is basically base times height divided by 2. So any triangle inside between these two parallel lines will always have the same area. So let's go on to prove this one here, the AB times AC times sine alpha over 2. We take this formula for quite granted, but proving these formulas before you use them is also very important. If we have triangle ABC and this one here is alpha, well, I'll use ABC because this will be easier to see. So I draw a perpendicular line from B to AC, and this angle here, let's say that this is alpha. Then the height of this triangle by trigonometry by SOHCAHTOA, H, which is the height, just basically equals AB times sine alpha, because sine alpha would equal H over AB. And we know that the area of ABC equals H times AC over 2, right? So if we plug this inside here, we would get 2 and then 2 in the denominator and then AB times AC times sine alpha. So first one true. Let's go on to the second one, which is about the incenter. If we have an incenter of a triangle, and we have the incenter which is here, but we know that if we draw a line from the center of a circle to each of its tangents, it always becomes perpendicular. Which means we can split this triangle into these 3 smaller sections. So ABC would equal ABI plus BCI plus ACI. And then each of the area of these triangles is basically R times base divided by 2. So if you apply each of that formula to ABI, BCI, and ACI, we would get R times, for ABI, what would the formula be?
BC times H.
Yeah. R times AB over 2. For this one, R times BC over 2, and R times CA over 2. And if we group all of these by R over 2, it just becomes R over 2 times sum of the R over 2 times the perimeter of the triangle. So second one also proves. Good. Everyone follow? Then the final one, not the final one, but the third one is about the excenter here. Sorry, terrible drawing, but A, B, C, and here's the excenter, the circumcenter, sorry. I always get confused. And then this length here equals R. So, but this one is actually derived from this one here. We will start from the formula we have there. AB, we will start from AB times BC times CA over 4R, okay? Okay. So let's think about only this triangle right here, BOC. We draw a perpendicular line from O to BC, which is just right here. Because we have an R here, and R is basically unwanted. We don't know how to express R. But we have BC, and we can actually express BC in terms of R times something else. So that's what we're basically going to do. We know that this angle here is alpha, right? And this angle here is 2 alpha, because if we have a circle and this angle is alpha, the angle of the circle to the center will be 2 times this angle. So because of that principle, if this is alpha, this becomes 2 alpha right here. But this one, BOC, is an isosceles triangle where BO equals OC, and therefore if we draw this perpendicular line, it would bisect this angle. So this angle basically would be alpha because this entirety is 2 alpha, and this is the angle bisector of BOC. So let's enlarge this one. Let's look at only this thing here. We know that this length is R, and this is BC divided in 2, and this angle here is alpha. Then using trigonometry, we know that sine alpha equals, what would this equal? BC over 2 over R, right? Because alpha is here, and we can use SOHCAHTOA to find out what sine alpha is. Then we rearrange this formula so that we represent BC in terms of other things. And then that becomes like this. And if we plug that inside here, it becomes AB times 2R sine alpha times CA over 4R. These two cancel out, which eventually just becomes the formula that we have right here. So this one equals the, so this what we initially started with. After some manipulations, we arrived at the sine alpha formula, which is the area of this ABC triangle right here. Are there any questions?
No.
Everything clear?
Yeah.
And then the next one, I am afraid that we won't have time for these two, the proof of these two. But this one, if you expand it, you can get the desired result. This one, if you use vectors and the cross products, you'll be able to prove this shoelace theorem right here. So finally, for the x-center, we also know that the center to a tangent is always perpendicular to tangent. So we can make perpendicular lines to BC, also the extension of AB and the extension of AC. And we can connect C with the x-center. And then what we can actually, and also this line here. So we basically connected all the lines to kind of find which kind of triangles that we have to evaluate in order to finally get ABC. And here, the really important thing to note is ABC here would equal this triangle plus this triangle. I'll use a different color. This triangle plus this triangle, and then if we subtract this triangle right here, then we would get ABC. Is that clear? So to put that into equation, ABC would be ABEA plus ACEA, and then BCEA is subtracted from it. But do you remember how I talked about what Oh yeah. But here you can see that the area of ABEA is basically equal to this length here times this length divided by 2. Because the area of a triangle is base times height divided by 2. So here this is the height, because this is perpendicular, and this is the base length. And therefore, for ABEA, it becomes AB times this one, this length here, which is the radius of the eccentric, which we define as RA, plus 1/2 times AC times RA, because that is equal to ACEA. And then we subtract this one, where this is also the height, and BC equals the base. Like this. So this is what we finally get. And then if we take out RA over 2 from each of the terms, we get AB plus AC minus BC.